So in a previous video, which I would link up either right or left, I looked at the effects of um, merging, combining, using Boolean to add your Boolean operation to add overlapping regions in a model versus when it is not merged together. So you can see here that we have these separate sub projects which were imported, and then you still have that the overlapping regions with this, they are not merged together. So this is a continuation of that video. So if you haven't looked at that, go check it out. So in the previous video, we looked at just the basic simple mesh, no refinement, anything. We just use these settings and we compare the results and saw that for the frequency. So wait a second, where is it? So this is not working. Wait. Let's see. So for the frequency, we had that the results between. Okay, so I copied the results from this into this, and so the results were pretty close in frequency. I mean, to correct to two decimal places for most of the frequencies. So we have just 5 modes here, and we saw a big difference in the external quality factor. So some varying up to an order of magnitude. So the model the same, just that for one of them we combine the overlapping regions, and then for the other I did not. So I mentioned in the other video that I'll do an adaptive mesh refinement, so that's what I went ahead and did. So I think I already mentioned it in some other video, but then adaptive mesh refinement, I turned this on, refined tetrahedral mesh, and then I use this setting: maximum frequency variation 1e to minus 6, number of passes, minimum number of passes 2, and the maximum number of passes 6. Now I could increase this because from the run we see that the number of passes was exactly 6, so it stopped. So that's the maximum, but then I don't think it got to this accuracy which I specified. So I don't think it did not I don't think it did not get to this frequency accuracy which I specified. But then just showing how the how maybe using mesh refinement could, or checking if using mesh refinement would actually make the results closer. So looking at the frequency, again we have that this is now for the adaptive mesh refinement. So this is a combined, which is from this model. So I did exactly the same thing for this and then copied the result. So this also had six passes, if you can see it here. So this is the results from pass 6, and then the delta, the df is 0.004. So I mean it's pretty close. 1 2 3 4 5 6 4 e to minus 6. Okay, so that's pretty close to 1 e to minus 6. Now looking at the two results for frequency, we have that, I mean, the frequency result were already close, but then now it's now correct to 3 decimal places. I think that's still poor. For this, it's correct to still the same 3 decimal places. This is also 3 decimal places, 3 decimal places for 6 passes. Yeah, that's pretty, I don't know, in my opinion, poor. I expected it to be better. But then with the frequency, the variation wasn't much to begin with. The problem we had, or the most variation, was with the Q factor. So if we look at the previous Q factor, we have this kind of variation. Sometimes when for the separate case it is the calculated Q external is larger, and then for the other case it's smaller, so it's just that. But then using the mesh refinement, we see that we start seeing kind of a convergence to a particular value, and then for the first 4 modes we do not have so much of a variation. So this is 1.7, 1.9, 76, 89. So and then this keeps increasing, so the difference between the calculated external quality factor keeps increasing until here where we have an order of magnitude. So the 5th mode, where we still have an order of magnitude difference. Refining the mesh further, like I said in the previous video, I expect to close this gap, but then it's like, is it really, I don't know. For me, I think it's already so much mesh refinement. The number of cells, the number of tetrahedrons we have here is 481,486, and yes, 489,226. So that's, I think, already fine enough. And then for the Q external, there's still this much difference. So yeah, I don't really know how. Okay, I think it's some complex. I mean, I can't really think of a simple way to explain, and don't understand it fully, to be honest, how the Q external is calculated. It's calculated from some complex. So when you introduce ports to your system, you have some funny business with your frequency becoming complex, and I think it's the ratio of the real part to the imaginary part, or imaginary part to the real part. So that's how the Q external is calculated. But the coding or the programming, what's in the black box, I have no idea. But then I would expect that the Q external should not be different. I mean, even for um, these two models, I would expect that it's not this difference, at least not up to an order of magnitude. This would be acceptable. I mean, even this, no, even this is kind of acceptable for mode 3, but then for this difference, it's yeah, too much. But which is however, I think that the reason, or one possible explanation, is also that these modes that I'm considering, they are trapped. So most of the time you don't trust the Q external in the first place, because ideally it should be, for an infinitely long pipe, it should be infinity. But then since it's exactly the same model, I would expect exactly the same result, or at least approximately the same result, even if the Q external is calculated is dependent on the length of the beam pipe, because we have exactly the same length here. So just mentioning that, I think that for modes that propagate into the beam pipe, you shouldn't have so much of a difference. Maybe I would have to check for that in a different video, so as not to make this video too long. So for the other ones, we compared the R over Q. So for the previous case, it was pretty close. So the longitudinal R over Q, and for the refined adaptive mesh refined, so the doesn't change. It's still pretty close. I mean, for this, it's okay, not even a decimal place, but at least the values are closer. Only for this mode do you still have some kind of difference in the R over Q. So there's that. Then for the transverse R over Q, you still have this kind of this difference, which I think, I mean, the values are really small, so it might not really affect, or at least for me, it doesn't really affect the end result of what I'm looking for, because if it's small anywhere, then the Q external also is small, then an impedance of maybe 0.01 and 0.05 is not really relevant for me, so I don't really care. So something that would be interesting would be to see how these values change, or how they behave for modes that actually propagate into the cavity, and that would be for another video. Then looking at the previous impedance, the longitudinal impedance, you see, because the okay, the R over K is quite close, and then for the old one, that's without mesh refinement, we had that the Q factor had this kind of pattern with one order of magnitude difference, and then this reflects in the impedance. I mean, you see the same pattern, but then you still have this one order of magnitude difference in the impedance, the longitudinal impedance. Now if we look at the for the refined case, yeah, you see that you have more closeness, and then this is, you could also see that it follows the same pattern as the external quality factor. And then here I think there should still be, yes, one order of magnitude, or approximately one order of magnitude difference. So whatever happens with the external quality factor is reflected in the impedance. Then for the transverse impedance, now remember that the transverse R over Q is also not, is also very different, and then the Q factor, the Q external, is also different. So they should also, yes, so you see it's also reflected in the impedance, the transverse impedance of the different modes. So you have that this is, yeah, so just something to keep in mind for me. What would be interesting would be seeing how these values vary. I mean, if it would vary, then I think that would maybe be some kind of, would it be a serious problem? Well, I think it depends on how much it varies. If it's one order of magnitude, then yes, I think that would be a problem. Or I mean, that's for me. But then also maybe this is already much of a problem for some applications. So I don't know. So just something you should take note of when yeah, running your simulations. And then you could, I think if you should refine this even further, you would be able to, I think in the limits they should converge to the same answer, but then this also takes, I mean, this 491,000 tetrahedrons, it would take also a lot more time to get to. So probably I might actually run one and like really refine it and see, or both of them, and see which of them tends to result the actual result, which would be the result in the limit, faster. So maybe we could recommend that, or maybe I could now recommend that, okay, if you have some imports, then try and as much as possible to merge the overlapping parts because it leads to better accuracy. I mean, that's not what I'm saying, but I'm saying that probably if I should run this a little longer and increase the number of passes for the mesh refinement, so refine the mesh and keep refining the mesh, then we see which one converges closer, fastest to the actual solution. Then one can definitively say, okay, this is better than the other. But for now, I still can't say which is better. Just so this video is just pointing out that these differences are there in the calculation. So you should maybe check your own figures of merit or whatever you calculate for in the post processing and see if it's so much different. I mean, if you're only concerned with frequency, or if I were only concerned with the frequency of the modes, then I wouldn't have a problem. Even without refinement, I already have that. Yeah, 2 decimal places, I'm okay with that. 2 decimal place accuracy, I'm okay with that. So that's that. So even with refinement with 6 passes and then increasing from, I think, what do we start with? I don't think the original mesh size was up to 100,000. I could check that. Something else. I could check that with the adaptive mesh. So mesh cells. So we started with 150,000 and now it's 480,000. So multiplied by 3 times 3. And so the solver time also increased to from about 200 seconds to 1,000 seconds, and then the error of course yeah, reduces. So I think I could. So the Q factor for the first mode, yeah, I mean, I'm not going to go through all of them in this video because that would take a lot of time. Maybe in some other video you could talk, and then you see that for this mode you have that the Q factor doesn't really converge to a particular value, and then this one also. But then maybe some other video, but then you could find out information about your adaptive meshing from this part of the navigation tree. So yeah, that was it for this video. Yeah, what should come next would be refining this further and seeing if it's yeah, converges, or you could do that on your own in case I do not upload a video. And then secondly would be checking for modes that actually propagate out of the cavity, so not modes that are untracked, and see what the values are. So yeah, that's it until next video. Bye.